All right, let's do some implicit differentiation today. This lesson is on how to implicit differentiate, what it is, how to do it, and whatnot. So first off, when you talk about implicit differentiation, a lot of students are not really sure what implicit means. Well, to first understand how to do implicit differentiation, what we first have to understand is what does it mean to differentiate with respect to x? Now, many times students kind of lose this in the definition of derivative, because until you learn the power rule and all the other rules of differentiation, you realize that y, the derivative of this function, which actually is known as an explicit function, or equation, I should write equation, all right, can be differentiated quite easily. What you notice is that this is going to be y prime equals 2x minus 5. We can figure that out by using the power rule and the constant multiplier rule and all those other cool rules that we have. Now, the thing that students don't realize is that actually when you take the derivative of this whole entire function right here, you actually are differentiating it with respect to x. And that respect to x is really kind of important because that is the variable that is changing. So when you take, for example, the derivative of y, we're actually taking and using the chain rule. The chain rule, taking the derivative of the outside, which is 1. So the derivative of that would be 1 times the derivative of y with respect to x, which we would say is dy dx. We then take the derivative of x squared. Well, knowing this, we have the derivative of the outside function, which would be 2x times now the derivative of the inside, which is dx dx. Derivative of x with respect to x. Now we don't write that because hopefully you realize that dx over dx is 1, all right, and then we just get our one value, oops, not that value right there. We then go over here and say, okay, what's the derivative of negative 5x? Well, that's going to be negative 5. Derivative of x, which is dx dx, which once again turns to 1, and we're left with is negative 5. And then the derivative of 2 with respect to x is still going to equal 0. And so we have our final answer, the same as we would do with the normal one. Now you might be thinking, well, okay, that's cool. Why do we need to know this with respect to x thing? Well, that changes when you have a variable that is not x as your main input, okay, as your independent variable. So for example, let's say we change this up, and now I put, instead of x, I put t. Well, with this, once again, it's an explicit function, but when I differentiate this with respect to x, we're going to take each function and take the variable with respect to this x variable. That's how it's going to change. So dy, derivative of y with respect to x is going to be dy dx. Now the derivative of t squared, well, that's going to be 2t. Times, remember the derivative of the outside is 2t, but the inside function is t. Well, what's the derivative of t with respect to x? Well, it's dt dx. dt dx. If we have negative 5t, well, it's going to be negative 5, derivative of the outside, times derivative of t, which is dt dx. And then that's going to be 0. So notice what we have is that each function is multiplied by the derivative of the variable with respect to x, just like we did above. Now, the reason why we bring this up is that this is used a lot with related rate problems, okay, when things change. All right, in this case, respect to time or respect of something other than what the actual variable is. And when we get talking about implicit differentiation, all right, it's important that we understand why we would use it. Right here, we have an equation of x squared plus y squared equals 9. This is what we call an implicit form. It's an implicit equation. An implicit equation, unlike an explicit, and you can see it on the bottom, explicit equation, is that implicit equations have the variables on the same side. So x and y are on the same side of the equation. So implicit means, all right, variables on same side of equation. So we can have a lot of different implicit equations. Lines can be implicit equations, quadratics can be implicit equations, a bunch of different things can be implicit equations. Now, this one happens to be x squared plus y squared equals 9, and that is the equation of a circle. If you recall x squared plus y squared equals r squared. We have an equation of a circle with a radius of 3. So we go 1, 2, 3, 1, 2, 3, 1, 2, 3. And I will attempt to draw a nice round circle. And that's horrible. But that's the equation we're looking for. Now, to do this, we want to differentiate this. And I actually want to find what is the slope at point 1 square root of 2, or 2 square root of 2. So if I plug in 1 in here, I have this point right here that I can find the derivative of. Now, one thing that's weird about circles, unlike regular functions, is that for every input there might be 2 outputs. And as a circle, we actually have a point at 1, which is positive, and we also have another point which is negative. Both give us different slopes. So just so you're aware, well, we're just going to find the slope here. Now, to do this, there's 2 different ways. We can do this explicitly, and we can do this implicitly. Now, explicitly, what we need to first do is take our equation, if you forgot what it was x squared plus y squared equals 9. We want to solve, usually, for what we're a dependent variable. So solve for the dependent variable. Solve for dependent. In this case, it would be y. So if we solve for y, we have 9 minus x squared. We take the square root, and we get y. But remember, when we take the square root, we bring a plus and minus. To create an explicit equation, notice how I have just one variable on one side, the other variable on the other. We create a function. We actually need 2 different equations. We have y equals a positive 9 minus x squared. This gives us a semicircle. If you look up here, this is a semicircle right there. The negative one, y equals negative square root of 9 minus x squared, will give us the bottom semicircle, and therefore gives us a complete circle. Now, if I want to figure out what is the derivative at the point x equaling 1, what I could do is figure out which equation has the 1 and then our y value, which is 2 square root of 2. Okay? Well, that would be the top one. So what we can do is we can actually differentiate this with respect to x and determine what that would be. So if we would do that, we would have derivative of y with respect to x was dy dx. We would then have this one where we're going to use the chain rule. This would actually be 1/2 times 9 minus x squared. It's a negative 1/2 power. Times the derivative of the inside, which would give us negative 2x. Just knowing that the square root of 9 minus x squared is actually equivalent to 9 minus x squared to the 1/2 power, just so we're aware where I'm getting that from. Okay, and differentiating that. We can then plug in our 1. And when we plug in the 1, we get, all right, 1/2. We have 9 minus 1 squared, which is going to be 8. Or 9 minus 1 squared, which is going to be 8. Then we have negative 2. This and this will cancel. We're left with a negative. On the bottom, we have the square root of 8, which is going to be negative 1 over 2 square roots of 2. Now, that is how you can solve this explicitly. One thing that's bad about explicit equations is that when you have explicit equations, you generally have, especially when you have circles, is you possibly can have 2 different equations that will give you a circle, which is kind of bad. To make this easier, what we could do is actually solve this implicitly, okay, or implicitly. When we use implicit differentiation, we're actually going to just take x squared plus y squared equals 9. And we're going to take this entire equation and take its derivative with respect to x. To do that, we're going to take the derivative of x squared with respect to x, so that's going to be 2x dx dx, which is going to be 1, plus 2y dy dx.
Natalie Schultz, please come.
I'm going to pause this for 1 second. Hopefully we don't have any interruptions, but continuing, we're going to have equals 0. Equals 0. All right, now, once we take this whole entire equation with respect to x, we now need to solve, and this is the key thing for implicit, we're going to solve for dy dx. Because notice that dy dx is not by itself, like in the other ones. I'm just going to scroll up here. Notice how when we solve this one, dy dx is all by itself. We have one variable in here, all right, for x, and now we're going to take this, all right, and try to solve dy dx so we can find what the derivative is, which is the slope. To do this, we're going to have subtract 2x. That's going to equal 2y dy dx. We're then going to divide by 2y, and we have dy dx equals negative 2x over dy, or sorry, 2y. If we simplify, we have negative x over y. This right here is an implicit differentiation equation. Notice how we have two variables, x and y. Now, if I want to figure out what is the equation, what is the derivative at x equaling y, or x equaling 1, and y is going to be equaling, we know 2 squared roots of 2. I need both points, all right, to be able to plug in here to get my derivative, my slope. Let's find out what it is. Negative 1 over 2 squared roots of 2. If you recall, that's the same equation we got when we did it explicitly. However, we didn't have to solve for y in the beginning. We just had to take the derivative and then just solve for dy dx and plug in our point. So this right here is the slope. All the way back, this is the slope of this line, this tangent line. That slope is negative 1 over 2 squared root of 2 using implicit differentiation. Well, let's try some more. Got 2 more for you. We're going to take this and we're going to try to find dy dx. Now, dy dx, once again, I graphed this for you. You can see if we want to solve this explicitly. Remember, explicit, you solve for y, or one of the variables. So in this case, we could solve it. We have y equals the cube root of 3x, so 1/3 power. We could take the derivative if we want to. Y prime equals 1/3 using the chain rule, 3x to the negative 2/3 power, times 3. Cancel, cancel. We have 3x all that quantity to the negative 2/3. That is what y prime equals. However, we could also take this and take the derivative implicitly. Okay? To take the derivative implicitly, we're going to take and have this 3y squared times the derivative of y with respect to x, which would be dy dx, equals 3 times the derivative of x with respect to x, which is 1. Solve for dy dx equals 3 over 3y squared. Simplify, 1 over y squared. What's an easier equation? I don't know, to each his own, but this right here and this right here are equivalent. Gives an equivalent slope. They don't look the same because this one is explicit. This one is explicit. Notice how we solve for x. This one is implicit because we just took the derivative regardless of which side it was on. So that's why we have a y in this one. 2 different slopes that will give you the same thing. Now, just to verify that, we can test this out. Because I want to figure out what's the equation of a tangent line at x equals 1. Equation of a tangent line at x equals 1. Now, to figure out the equation of a tangent line, we need a point and we need a slope. The slope is the derivative. That's dy dx. The point we know is going to be 1. Now we got to figure out our other points. We're going to plug in 1 in here. So it'll be the cube root of 3. Cube root of 3. So now to figure out our value, we're going to take our point and plug it in there to find our slope. So we can use this to find our slope. I'm going to use this one first. We'll have 1 over y squared. So it'll be the cube root, or 3 to the 1/3 power, I'll do that, squared. That slope is going to be 1 over 3 2/3. Right? 3 2/3. So our equation of our tangent line, y equals 1 over 3 to the 2/3 power times x minus 1 plus the cube root of 3. That's the equation of tangent line at 1. Look at that right there. That's the equation of that tangent line. Just to verify that this slope would actually give us the same thing, let's plug in 1 into here. We'll plug in x. X is going to be 1, so when we plug that in there, we actually have 3 to the negative 2/3 power, which is equal to 1 over 3 to the 2/3. What do you know? They equal the same thing. Now, so that's how we find the equation of a tangent line. Now, one other additional thing I just want to point out is that sometimes, this is new information, so make sure you write this down, is that sometimes you'll be asked to find the equation of a normal line. A normal line, now you might be thinking, hey, all lines are normal. They're all straight, right? Well, they are. However, a normal line, when we refer to this, refers to a perpendicular line. Perpendicular line to the tangent. To the tangent line. So the perpendicular line. Perpendicular lines are 90 degrees. So over here, I'm looking for a line that passes through this point that is perpendicular to this. So I'm looking for that equation, a 90-degree angle. To do that, once again, it's an equation of a line. I need a point, and I need a slope. The point is going to be the same, 1, and it's going to be, what's our point? The cube root of 3. Our slope, well, if you recall, perpendicular lines from algebra 1 are opposite reciprocals. Opposite reciprocals. So perpendicular lines, if you have the slope right here, the perpendicular slope would be the opposite reciprocal of that slope. So that's pretty easy. That's our slope right there. Y equals the opposite reciprocal of that, so be negative 3 to the 2/3 times x minus 1 plus the cube root of 3. Opposite reciprocal slope. And that's our normal line. That's the line that is perpendicular to the tangent. Okay. Learn a lot of information. We talked about implicit. We talked about tangent lines. We talked about normal lines. What we're going to do is we're going to do one more problem, and then you can do some homework and try this out on your own. And there might be some other additional tutorials or lessons on this on the line. But let's try this one. Okay? We're going to find x squared plus xy minus y squared equals 1. Now, this right here, if you're not familiar, if you go on to, there's a graphing websites that do implicit equations. Now, this is implicit because all the x and y's are on the same side. So this is implicit. You notice you have x and y's all on the same side. This is a hyperbola. Hang on one second. So what we're going to do is this actually is a hyperbola that's on a slant. Okay, so slanted hyperbola. Something that you really haven't seen is a little complex. Now, this one we have to solve implicitly. All the other ones we try to solve for y. Now, if you try to solve for y in this one, that would be almost very difficult. I won't say impossible because nothing's impossible to God, right? However, this would be very difficult algebraically to do. So we're not going to do that. What we're going to do to find dy dx is we're just going to take this and do this implicitly. Now, here we go. First off, we're going to take the derivative of x squared, which is 2x. With respect to x, it's just going to be 2x. Next thing we're going to do plus, I'm going to change the color here, x times y. Now, x times y is a product of two functions, x times y. So what we have to use is actually the product rule. We have to use the product rule. So what we're going to do is we're going to take, I'm going to just put this, so we're going to use the product rule here. Derivative of the first, which is 1, times y, plus now the derivative of y with respect to x. And that's going to give us dy dx. My dream is that those that are watching this are seeing that in their heads or as they're following along. So dy dx times x, which is finished in product rule. Minus, my original color, minus the derivative of y squared. Well, y squared with respect to x is 2y times the derivative of the inside, chain rule, remember, dy dx equals now the derivative of 1, which is 0 because it's a constant. Now, once we take our derivative, now we need to solve for dy dx. Make sure you do that. Solve for dy dx. So we're going to take all the non-dy dx's, we're going to put them on, so we're going to segregate. It's okay in this case. We're going to take all the ones that don't have dy dx and put it on the other side of the equation. So we're going to have y, all right, so on this side, what's left over, dy dx times x. Let me get rid of this. It's distracting me and probably you as well. All right. We then have minus 2y dy dx, which is still there. And that equals negative 2x minus y. We're going to take these two right here and subtract from the other side. Next thing, one of these things is just like the other. What can we factor out? dy dx, yay! We factor out dy dx, and we have x minus 2y right here. And now, le test de résistance, la fin, is we are now going to solve for dy dx by dividing by x minus 2y. So we have negative 2x minus y divided by x minus 2y. And that's our derivative. Ta-da! Now, if we want to go one step farther, we can find the slope of the tangent line, or lines, at negative 2. Now, if you look at the graph, negative 2 is located right here, and you realize that I have a point here and a point there. Well, let's try to find those two slopes. Now, to do that, I'm actually going to borrow this. I'm going to take this along with me, because this is our original equation. Okay, we have our derivative. Now, the one thing, in order to find the slope of the tangent line, I need to plug in, I need an x and a y value. I only have an x value. I need to find the y value. To find the y value, we need to plug the x into the original equation. Okay, so we need to find y. It's like finding Waldo, but completely different. So we have 4 plus negative 2 times y minus y squared equals 1. Notice this is a quadratic. I'm going to make this y squared positive. So I'm going to add to the other side and put everything on the other side. All right, so we're going to use all the algebra skills. So we're going to have negative 4 on the other side is going to be negative 3. I'm going to add this 2y over here, and I'm going to add y squared. From here, we can simplify this, and what we have is y plus 3, y minus 1, and that will equal 0. So y is going to equal negative 3, and y equals 1. So for both, we have 2 different points we need to plug in, because we have 2 different lines. We have one, x equaling negative 2, and y equaling 1. We have x equaling negative 2, and y equaling negative 3. And we're going to plug each one of these into our derivative. The first one, dy dx for the top line. We have negative 2 times negative 2. So I'm plugging my x right into here. Minus our y, which is in this case 1, over negative 2, which is my x, minus 2 times my y, which is 1. We have 4 minus 1, which is 3. We have negative 2 minus negative 2, which is, minus 2, which is negative 4. So negative 3/4 is our slope for the top function. Does that make sense? Yeah, our slope's going down, so that makes sense. Let's go to the bottom one. The same thing. Change my color. We're going to have dy dx in this case, negative 2 times negative 2, minus this y, which happens to be negative 3. All over negative 2, which is my x, minus 2 times my y, which is negative 3. Look at this. 4 plus 3, which is 7. Negative 2, we have plus 6, which is going to be 4, so 7/4. Positive 7/4, and that makes sense because it's increasing positive 7/4. So, that is our implicit differentiation. We use all the same properties. We use chain rule, Key things when you're doing this is remember, what are you taking this with respect to? Okay, what are you taking with respect to? You do the same thing for finding tangent lines. You need a slope and a point. And one final thing is that we talked about normal lines. Normal lines are perpendicular to the tangent. So that was our lesson for today on implicit differentiation. We'll have several more of these lessons to get better. But here is your homework assignment, which is located on the board, and go get them. The homework assignment, though, is a lot of chain rule and also has some implicit differentiation when you get started with that. All right. Well, good luck with it, and God bless. And have a great weekend.